Now we go into the understanding of module 4, and the contents of module 4 are as follows. So here we will look into sequential circuit design and dynamic logic circuits. In the earlier topic, that is module 3, we had a discussion on combinational circuit design. Right now we are considering the sequential circuit design, which is based on one input following the one input giving us the output, and that output is fed as input to the next circuit. So the basic topics involved in sequential circuit design is it requires memory, and the circuit design, it is the important concept used here are the latches and the flip-flops. And next you have dynamic logic circuits. So this is almost the same as your CMOS, but then extended version of CMOS here with the influence of the capacitor being introduced here. So that is what we will be discussing here in the next topic. Next topic is dynamic logic circuits. So what exactly is dynamic logic circuits? What is it we are going to focus? Introduction, basic principles of pass transistor circuits, synchronous dynamic circuit techniques, dynamic CMOS circuit techniques. So these are taken from the first text, that is Sungmo Kang, and it is especially with the 9th chapter, and these are the different articles. So we will be focusing on dynamic logic circuit. So we need to understand what you mean by a dynamic logic circuit. So after understanding dynamic logic, we'll now little uh, hold the contents with dynamic logic and shift on to the topic, which is with respect to the pass transistor circuits. So what exactly is a pass transistor circuit? The input is given at the source or the drain, and subsequently the output is collected at the drain of the source. And it is the gate is not the place where we are giving the input. So normally at the gate we give the clock signal. Therefore, we have the diagram shown below. The fundamental building block of NMOS dynamic logic. So dynamic logic is this much, consisting of an NMOS pass transistor driving the gate of another NMOS transistor. So this is the pass transistor which is driving another NMOS transistor. So this is the concept of dynamic logic. And whenever, please remember, dynamic logic, the two core ingredients are, one is the clock and the other one is the capacitor. So this and clock and the capacitor will be forming the core ingredient of dynamic logic. It is dynamic logic. Therefore, you have the clock, you have the capacitor here. So let us now understand how this works. The pass transistor is given here as MP, is driven by a periodic clock signal. It is driven. So since the gate is given to the clock, the help only when the gate is 1, the information at the source is passed on to the drain. If the clock is 0, it merely acts as an open circuit. No information from the source will reach the drain. So the pass transistor MP is driven by the periodic clock signal and acts as an access switch to either charge up or charge down the parasitic capacitance C depending on the input voltage V in. So what is the summary of this statement? When clock is equal to high, the transistor is closed. The switch is closed. As a result, whatever the logic voltage you have applied at V in, let us say 0 volts, same 0 volts is passed at the node of the drain, and that in turn is Vx. So this is with 0 logic. Next, when clock is equal to 1, you can assume like this. Yeah, it's already shown there, written there. When clock is equal to 1 and V in is equal to 1. When clock is equal to 1 and V in is equal to 1, both are high. Therefore, the switch is closed. Whatever is high VDD, whatever is logic 1 means it is your VDD 5 volts. This is successfully passed at the drain. This is successfully passed at the drain. So what will be the voltage at Vx? Voltage at Vx will be 5 volts if I assume. And the moment it is 5 volts, the node at Vx is 5 volts, capacitor is charged to the maximum. Capacitor is charged to the maximum up to 5 volts, and it will decay only if this switch is on. It will find a path to decay, go to the ground. So let us see that understanding later on. So that is the summary. So either it will charge up or charge down. And similarly, when the V input is not 1, instead it is 0, it is an open circuit and there is no potential for the capacitor to charge to the maximum. It will decay on its own and as a result it will discharge. So it is going down. Therefore, the capacitance charge and discharge is completely dependent on V in. Thus, the two possible operations when the clock signal is active are the logic 1 transfer, charging up the capacitance Cx to the logic high level, and logic 0 transfer, charging down the capacitance C9 ante, C9 alla, this is Cx, going to the logic low level. In either case, the output of the depletion load, so this is the load. Depletion load NMOS inverter obviously assumes a logic low or a logic high depending on the voltage Vx. So when it is 5 volts, high voltage, this is your gate, therefore the switch is closed. Switch is closed, entire VDD will come here and wherever you are trying to measure your output respectively, you will get your, so this is your drain, you will get your output. Your output would be 1 because your V volts is 1. If this is 0, it acts as an open circuit, your output would be 0. So this is how the basic principles of pass transistor is used along with the dynamic logic. So in dynamic logic, please remember it is a combination of clock and capacitor. So notice that the pass transistor MP provides the only current path to the intermediate capacitive node. Yes, with the help of your transistor MP, only it is possible to have the current path to the intermediate capacitive node. That is the only path for the node V at X to have its voltage. So when the clock signal becomes inactive, when clock is equal to 0, the pass transistor ceases to conduct. Just now we have seen only the case when the clock is equal to 1, the pass transistor is on and whatever is at the source will pass on to the drain. What if the clock is 0? If the clock is 0, the transistor is in off state and no information from the source will pass on to the drain. So pass transistor ceases to conduct and the charge stored in the capacitor continues to determine the output level of the inverter. So till the duration the charge is stored in the capacitor, you will be getting the respective output. The moment gradually the capacitor discharges and the moment the charging capacity of the capacitor is reduced or going towards 0, subsequently the transistor at the depletion load is an open circuit and that in turn would have an effect on the output which is going to 0. So that will determine the state of the output level of the inverter. So this is how it works with dynamic and transistor logic. So next we'll examine the charge up event. Now we'll go ahead trying to understand further. So when it is logic 1 transfer, already we have had a brief understanding about how logic 1 is transferred. Let us have again, assume that the soft node voltage is equal to 0. That is Vx, soft node Vx, T is equal to 0 is 0 volts. So initially nothing is there and Vx is 0. A logic 1 level is applied to the input. So to the input, this is the input and the logic is 1. So 1 corresponds to high voltage. In other words, it is nothing but VDD. Now the clock signal at the gate of the pass transistor. Now the clock signal here at the gate of the pass transistor goes from 0 to 1. 0 to 1. What do you mean by 0 to 1? Again, the gate is on. It can be seen that the pass transistor MP starts to conduct as soon as the clock signal becomes high, and that MP will operate in saturation throughout the cycle. Since the voltage is equal to the gate voltage, VDS is equal to the gate voltage, the device goes into saturation and same amount of current flows till this interval. Therefore, the drain voltage is greater than VGS minus VT. The drain voltage is at a higher potential. It is greater than the gate voltage minus the threshold voltage. Therefore, the circuit to be analyzed for the logic 1 transfer event can be simplified into an equivalent circuit. So, as I told, this is going into saturation and same amount of current flows. This current is a strong current, saturation current, highest current, and that in turn will charge the capacitor here to the respective voltage at this node Vx. So what is the voltage at this node? This is one on switch. Your VDD, entire VDD comes over here. So the voltage at Vx would be VDD, capacitor would be charged to VDD. Therefore, what was the logic? 1. What is the logic present at 1? At Vx? 1. Therefore, we are successfully able to transfer logic 1 with the help of this equivalent circuit. On the same grounds, we will now understand logic 0 transfer. So 0 transfer is low voltage or ground. Assume that the soft voltage at V is equal to a logic 1 level initially. So assume it V is equal to logic 1 level initially. So earlier state V here would be 1. A logic 0 level is applied to the input terminal. This is 0, please. This is 0. You can have a note, yes. A logic 0 level is applied to the input terminal here, which corresponds to the voltage as 0. At this particular input, you have your input equal to 0 volts. Now the clock signal at the gate of the pass transistor goes from 0 to VDD. From 0, it goes to VDD. Clock is 1. So clock is 1 and it is in short. What happens? Whatever is the logic present here will be passed here. So the pass transistor MP starts to conduct as soon as the clock signal becomes active, and the direction of the drain current flow through MP will be opposite. So this is how the drain current flow will be, because it is 0. It is 0, this is 1. From 1 to 0 current flows from high potential to low potential. So the current flow will be opposite to that one which was already existing. So when the current flows, this is logic 0, and that is how the input 0 was successfully transferred at this particular node. This means the intermediate node X will now correspond to a drain terminal of MP, and that, yes, this obviously is nothing but the drain terminal, and that the input node will correspond to the source. Yes, this becomes your source, this becomes your drain. Very much pretty sure about this. With VGS, that is between gate and the source. Source is at the low potential, and you give high. This is what is VDD, high. Then what happens between VDS? Since this is high, it is on, and the voltage for one interval of time VDS would be Vmax, because pass transistor operates in linear region throughout the cycle. Since VDS is less than, so VDS is less than VGS minus VT. So it is in linear region. It is completely dependent on how much voltage you are applying, that much of output voltage you are getting. So the circuit to be analyzed for logic 0 transfer event can be simplified in an equivalent circuit as shown. So as in logic 1 transfer case, the depletion load NMOS inverter does not affect this event. So once the current is flowing, we can say that it is flowing in this direction. Therefore, this gradually goes down to 0.